there is no any single answer because these are just points, and we have some visual perception. 2 is also good, 3 is also good. Although you see the description that in reality there are 3 distinct classes. About what reality we are speaking, no one knows, because in reality maybe we have 2 clusters, in reality maybe we have 3 clusters. However, you understand that clustering unsupervised approach is always a problem. There is no unique single answer how many clusters finally we need, because exactly we need to understand our application. We need to have some expert knowledge about this application. In this case, we have just points without any description, so there is no big difference. 2 or 3 clusters we will finally get, but it should be very interesting to follow how hierarchical clustering is just performing clustering for these observations. And here we have, last time I showed you that when we are constructing the corresponding dendrogram, this dendrogram is actually giving us more data understanding capabilities, because before, if you can visualize, you understand how many clusters you need. But this is, you can just apply for 2-dimensional case. When you have multi-dimensional case, you don't have any visualization opportunities. So you can just draw the corresponding dendrogram, because independently how many dimensions you have, you always have dendrogram, and dendrogram is showing the distances between observations and between the clusters. So it's giving us better data understanding features. Now you see that even if you don't have this visualized picture, when you have some understanding of how many clusters you have, when you are drawing the corresponding dendrograms, you are understanding some features of your data, and you can just think from where to cut this dendrogram to get the corresponding number of clusters. So the first picture is showing that you have the dendrogram without any cutting, so you have only one cluster, all observations together. Then you see this dashed line, straight line. It's showing, so when you are cutting your dendrogram with similarity, what we have here, this is something within 8 and 10, maybe cutting exactly from 9, you are getting 2 different clusters, and these clusters are shown in 2 different colors. Some of the observations, you see these observations in the corresponding leaves. These are red observations, and here we have green observations. The overall dendrogram is showing how those observations are connected by distance with each other. And when you are cutting, you are getting just exactly two clusters. And dendrogram is actually indicating that here the best solution can be 2, or here 3 clusters, nothing else, because when you are going to cut with similarities, smaller similarities, you see here the clusters are very close to each other. Of course, you can cut into 4 clusters, you can cut into 5 clusters, but you see that these clusters are very close to each other. And if you think in terms of, again, within cluster variation, what you are trying to do here, that for a single cluster, the within cluster variation of this cluster observation must be always small than within cluster variation jumping from one cluster to the other. So you need something isolated clusters. You need isolation, localization. That is why when you are going to cut with smaller dissimilarities, you are just mixing different clusters together. So in this picture, it's better to cut for 3 clusters, or it's better to cut for 2 clusters. Nothing else we can see. And this dendrogram is actually giving us data understanding. This dendrogram is showing how close are our observations to each other, and indicating how many clusters we can get by cutting different similarities. And here we have another example. So you see here again, special clustering. Two features, x1 and x2. Here we have coordinates, so Euclidean distance we can use. So from where we are starting? We are starting with pairwise distances, all possible pairwise distances. And you see that 5 and 7 are the closest. That is why we are starting with this small cluster. From the other side, we have 6 and 1. So 6 and 1 together with 5 and 7. Then 8 is the closest point to this 5 and 7. So we are connecting these 3 points here, you see, with the corresponding dissimilarity. Then 2 is coming together with this cluster. Then 9 is coming. And separately, we have 1, 6, 4, and 3 together. Then you can just actually merge these two rather big clusters, getting the final one very big merged cluster containing all possible observations. Again, all calculations we are performing hierarchically, starting with the small single observations, 1, then 2, then adding some other observations. And this is from bottom to top. In the top, we have only one very big merged cluster, which is containing all possible observations. Yeah, go ahead.
Can I ask a question?
Yeah, sure.
In the second graph, x1, x2 depending on x1, how do we get those coordinates? Are they the centroids or the averages of the observations?
Which coordinates?
The x1 and x2.
Yeah, these are our points.
Yeah, like for example, the coordinates of the cluster 1.
There is no coordinates for cluster. There is coordinates only for observations. So
yeah, on the graph, like these minus 0.5 and minus 1, where do we get those?
You have these points. Someone gave you the corresponding data frame with features x1 and x2. You have the corresponding numbers. You think just your observations are coming like a point. Each point has a coordinate. You already have the right figure. We just visualized it. This is your data frame.
Okay.
Actually, in this case, you have 9 different observations. So your data frame includes 9 rows, and you have 2 features, so 2 columns. The value of x1 is showing the corresponding x coordinate, and the value of x2 is corresponding to y coordinate. You're just putting the corresponding points just to visualize them. Not always it is possible, because not always your data frame is containing something like a spatial coordinates. But usually when we are speaking about clustering, we always, not always, but in many cases, we mean spatial clustering, Tarascan clustering. So we are assuming that we have some points in an n-dimensional space, and the corresponding values of features are the corresponding coordinates. And just we are trying to isolate based on some clustering those spatial points. But not always it is reasonable, because maybe we have data that are not corresponding to some coordinates. But you need to somehow decide about the distances. For example, you can have I am always bringing this example, you can have not observations, but you can have, for example, matrices, you can have pictures. So you have 2 different pictures. How you are going to define the distance between these pictures? It's always problem. If you can do it, then you can go ahead with with the corresponding clustering, because in clustering the only thing you need is just to understand how you are calculating the distance between 2 different observations. Now let's go ahead. So here we have visualization of this picture. Sorry. So we have here 2 clusters, 5 and 7, then 6 and 1 together. So we are starting to grow our dendrogram from bottom, from leaves. Leaves are 1 and 6, then 5 and 7. We have 4 different leaves. Then we are merging this 5 with 7 and 6 with 1. Then we are, okay, sorry, I just jumped. Then here you see, then 8 is merged with 5 and 7, then 2 with this blue cluster, then 9 is coming, And you saw as bigger and bigger are our clusters becoming, as farther the corresponding points. That is why in the corresponding dendrogram, the similarities are growing when you are going from bottom to top. And when you are just cutting from somewhere, actually you are saying that I know that within my clusters that I am getting, which will be the maximum distance between different subclusters. So when you are cutting from, for example, by 2 here, you know that within each cluster, the maximum distance can be, for example, here 1.7 and here 1.2 or 3. So when you are cutting from somewhere, you are controlling the distances of your objects within each cluster, which is rather good indication of good or bad clustering. And you now understand why we are calling it as hierarchical clustering, because we are starting with smaller clusters, then growing this cluster by adding new and new observations. And finally, we are getting one very big cluster containing all available observations. Okay, now returning to our big problem. Even when you know how to calculate the distance between different observations, for example, in this case, if you have coordinates, Euclidean distance is working, it's very difficult to say how we are calculating, for example, distance between this 8 and between the red cluster that we have. So we need to come up with some ideas and with non-unique ideas. So there are different possibilities how we can perform this distance calculation. And in case of hierarchical clustering, this is known as linkage. So when you see linkage, then it is describing how to calculate the distance between different clusters. For example, here 5 and 7 as a separate cluster, and you are trying to understand, can you merge 8 with this cluster or no? If they are close, you are merging. If not, then you are waiting. So ideas here can be different. At least you see here five different approaches. Our sklearn library has all those possibilities. So we have complete linkage. This is just one way of calculating the distance between clusters. We have single, we have average, we have centroid, and we have word linkage. So 5 different linkages. So these are classic standard linkages. Usually default, as I know, default in sklearn is word linkage, because this is giving us the same as within cluster variation in case of k-means clustering. And when you are using this word linkage, the results that we are getting are very close to the results of the k-means clustering, because k-means clustering is also trying to use this within cluster variation. And when you are using dendrograms, this is not exactly the same, because they are totally different in their ideas. But however, when they are trying to minimize the within cluster variation, objective function results are becoming very much similar. And this is the default, but you can actually change it. Now let's try to understand, for example, complete linkage, how we are calculating the distance between two clusters. So this is known as maximal intercluster dissimilarity. So maximal term is exactly indicating that when you have two different clusters, so you see we are computing all pairwise dissimilarities, means pairwise distances. So you have cluster 1, you have cluster 2, cluster A or cluster B. Within each cluster you have some points. So you are picking these points and calculating all possible distances of the observations from A to B, and record the largest of these dissimilarities. That is why here we have maximal intercluster dissimilarity. So complete linkage is actually returning the maximum distance from all of the distances that we have within the observations from cluster A to cluster B. Even if these clusters are rather close in terms of some points, you are always returning the maximum points. If you have two outliers which are very far from each other, and one is from cluster A, the other is cluster B, complete linkage is returning this biggest distance. And you understand, if you have the biggest distance, you can have the smallest distance, then you can have the average of all those pairwise distances. Each one is describing one of our linkages. So complete linkage is giving us the maximal distance within these pairwise distances. Then we have single linkage. Single linkage is giving us the minimal intercluster dissimilarity. So again, computing all pairwise dissimilarities between the observations in cluster A and the observations in cluster B, and record the smallest of these dissimilarities. So maybe for some kind of problems you need the smallest, some kind of problems you need the biggest. No one can say which one is the best for your specific application. If in your application you have many different outliers, then we understand that biggest will not work and smallest will not work, because if there are a lot of different outliers, so you are always getting rather small and rather big distances between the cluster, but in case of outliers, no one will work. So in this case, we have average linkage, mean intercluster dissimilarity. So we are computing all possible pairwise dissimilarities between the observations from clusters A and B and record the average. This is better when you have some outliers, because when you are averaging, then you are averaging also across all different outliers. So we can take the maximal distance within these pairwise distances, the smallest, then we can take the average. Then here we have centroid linkage. Centroid linkage, you understand, for each cluster, we are calculating centroids similar to k-means clustering. So you are taking the observations, calculating the average, getting a single point and saying that this is your centroid. And then you are calculating the distance between these centroids. So totally different idea compared with the previous three ones. So you see that where we have this application, genomics. So usually centroid linkage is used in genomics, or maybe in other applications when this is more appropriate than the previous ones. So it's interesting to compare with average linkage. So average linkage is calculating all possible pairwise distances for the observations from A to B, and then averaging all these distances. In case of centroid linkage, we are just calculating the averages of observations within each cluster, getting single centroids for each cluster, and then calculating the distance between these 2 points. So totally different approach. Then we have ward linkage. Ward minimizes the sum of square differences within all clusters. It is a variance minimizing approach, and in this sense, it's similar to the k-means objective function. So they are working similarly. So you understand that ward linkage in this case working in the same way. So we have within cluster variation. Within cluster variation, we are calculating for each cluster. How we are calculating? We are calculating centroid for each cluster, then calculating the sum of square distances of all observations within this cluster from the centroid, just summing all these distances, and then we have total within cluster variation. So ward linkage in case of hierarchical clustering is just trying to minimize the overall within cluster variation, exactly in the same way as k-means clustering is performing. So we understand that although the objective function is the same, but the results should be different because the procedures are different in case of k-means and in case of hierarchical clustering. But in many cases, So as we are using the same objective function and we are trying to find its global minimum, then the results are somehow comparable. Then we have some linkage properties. You see that we have five different linkages, and for a specific application, it's very difficult to understand which one to use. But there are some general properties connected with these linkages. So we have some also properties with this agglomerative clustering. You see, agglomerative cluster has a reach, get, richer behavior that leads to uneven cluster sizes. Reach, get, richer means that if you have rather big cluster, then more observations you are merging with this bigger cluster. So when you have rich cluster, so it's becoming richer and richer. This is one of the disadvantages of this agglomerative cluster. And when you are using single linkage, so it is the worst strategy. And WARD is giving most regular sizes. So when you are growing your dendrogram, you are trying to get something like a balanced tree. So when you see balanced tree, it's better than unbalanced tree. And as agglomerative clustering has this disadvantage to connect observations to the bigger cluster, it's better to use linkages which are trying to somehow balance the trees. That is why single linkage, you can just try to recall single linkage is using the minimal intercluster dissimilarity. So even when you have 2 points which are close, rather one to the other, coming from clusters A and B, you are exactly merging these clusters, because in this case you are taking this minimum distance. It's rather bad. It's better to somehow average the distances that you have than only after we decide which one to use. That is why the single linkage is always leading to some unbalanced dendrograms, and then it's very difficult to understand from where to cut these. So that is why word distance is the default in sklearn. By default, we are using this word distance. And also sometimes we are using this complete, not complete, but average linkage is also giving some moderate balanced trees, because it's just calculating the average of the distances that we are getting. So, but as usually, so together with advantages, we have always disadvantages. So you need to try different approaches. So you see single linkage, while not robust to noisy data, because we are calculating minimum, or in other case, we are calculating the maximum. As I said, in case of noisy data, it's not very proper way to calculate the corresponding distances between cluster. But you need to understand that together with these mathematical ideas, we have also implementation problems. You need to write the corresponding codes in Python or in some other languages, and you need to have some optimal implementation. So not all linkages are just leading us to optimal implementations. So here we see that single linkage, although it is not working very well, but can be computed very efficiently. So you see two sides: implementation complexity versus some advantages or disadvantages of the corresponding linkages coming together with some noise. And also you see that single linkage can also perform well on non-globular data. This is also interesting. Now just you see here the same number of points, the same kind of observations with different linkages. I showed this last time. Let's again go through it. So you have average linkage, then you have complete linkage, and you have single linkage. So visually try to compare which tree is more more balanced. What does it mean, balanced? So when you are cutting into different clusters, you are expecting to have almost similar number of observations within each cluster. When you are cutting and see that within this cluster you have 2 observations, and within the other cluster you have 1 million different observations, this is bad, because you have something like an outliers in a cluster, then the remaining points just in the other cluster. This is very bad. So when you are cutting the tree, you are expecting to see similar number of observations within different clusters. And you see that in case of single linkage, you have just very, very unbalanced tree, because when you are cutting, you are cutting one point in a cluster, then the other points to the other cluster. This is very bad. So you see that much more balanced trees we are getting in case of complete linkage, because when you are cutting here, for example, you are getting just rather 2 big clusters. When you are cutting more, then you are getting clusters with similar number of observations. Although also here we have some imbalanced clusters, because you need to understand that not always you can come up with the right number of clusters that you need. So in case of complete linkage, usually we are getting balanced dendrograms, and it's much easier to understand how many clusters we need. You see the problem with single linkage. All distances are rather close to each other, and you cannot realize from where to cut because they are very dense. And when you are cutting, you see after each cut you are getting some outliers, and then the remaining part in one single cluster, which is rather difficult to interpret. While in case of complete linkage, you see such a sparse domains from where you can cut. You can get just 2 clusters. From here, you can just get 4 different clusters. When you are getting 4 different clusters, you are getting 2 clusters with similar number of observations, then one small cluster, then bigger cluster. Although you see that again, not very well balanced, but much better than compared with the single linkage. And the same problem in this case with this average linkage, bad imbalanced dendrogram. Again, when you are cutting from here, you are getting this small cluster, then the bigger cluster. So we are always trying to use linkage for these specific observations, which are leading to some more balanced trees. That is why usually when you are working with codes, try different linkages, then visualize if it is possible, because not always possible to visualize this dendrogram in case of many different observations. When you have millions of different observations, you are unable just to show all those observations in your picture. But however, try to somehow come up with this visualization to see which linkage is the best. Then some new ideas connected with how you are actually calculating this dissimilarity measure. This is the most important Okay, so we have this picture trying to explain that. Can you see my screen?
Yes.
Okay.
Yes.
So this is trying to explain that we have problem with distance calculation. It's, as I'm always saying, application specific. For different applications, distances can be different. And in this case, you see one interesting example showing the distance between two time series data. We have 3 time series data. So you can think that one of the features is actually indicating the time. So you see, when you are calculating the distance as usually as a Euclidean distance, so you are capturing time series which are close to each other. These two time series are very close to each other. But not always it's natural. So you see there is a way to calculate the distance between two time series as a correlation. You see this green one and this below yellow or brown one. They are rather far from each other. So when you are calculating the corresponding Euclidean distance between these two time series data, you are getting rather big distance. But what is interesting, when you are calculating the correlation, so correlation is actually showing similarity of behaviors. So when one is going down, the other also going to down. Then one is going up, the other is also going up. So they are, you see, they are correlated, increasing, decreasing simultaneously. So although the Euclidean distance can be rather big, but this correlation coefficient can be rather small. And for different applications, maybe better to use correlation than Euclidean distance. So this is just to indicate that for different applications, you need different distances. Not always there is a natural way to understand which distance to use. Sometimes you need to come up with some interesting ideas. But however, be aware that, as usually in case of clustering, the main problem is distance calculation. When you have some special clustering case, Tarazakan clustering IDEPCA, then everything is as usual, Euclidean distance will work. Otherwise, you need to decide how to calculate the distance between observations. So what we have here, something like a conclusion, some questions here. So should the features first be standardized? This is just a common question for all possible kind of ML algorithms. So when you are doing something in ML, the first question is coming, do I need to standardize, scale, or normalize observations or no? So there is no unique answer, yes or no. You always need to try both cases, both scenarios, and to come up with final decision. So in case of hierarchical clustering, as we said, we need to understand dissimilarity measure, then we need to understand what kind of linkage to use. The most important questions, then if you have the corresponding dendrogram from where to cut, which is the similarity based on which you are going to define the number of clusters to use. And in case of k-means clustering, we need to come up with the same idea, how many clusters we need. Although in case of k-means clustering, we are deciding about the number of clusters before starting to do the clustering, while in case of hierarchical clustering, we draw the corresponding dendrogram and only after it deciding how many clusters we need. So this is the main difference. Okay, as usually, try several different choices, then come up with final decision. There is no single right answer. And again, the problem is, as this is not a supervised problem, this is unsupervised problem, the final conclusion is always very, very hard to perform. And here you see, be very careful, because you don't know how to interpret mostly your results. Because if this is not a supervised problem, you don't have labeled data, you don't have teacher which can say when you are right, when you are wrong. That is why always it's very difficult to work with unsupervised learning rather than with supervised, because in supervised case you have a lot of different measures that guiding you towards the right, correct answers. And here final just slide showing different data sets. You have this picture in your Python codes that I uploaded. So you see we have 1, 2, 3, 4, 5, 6 different data sets. Some circles we have, some blobs, transformed blobs with the same standard deviations or with different standard deviations, then just one very big set of different random points. And here you see dendrogram with different linkages: single linkage, average linkage, complete linkage, word linkage. You see, although we said that single linkage is not always leading to balanced trees, but you see only this one is working in this case. So average, complete, and word linkages are not working. You can imagine why. Because let's remember when we said how k-means clustering is working, we indicated that we need some complex, such convex shapes. We need some blobs. And you see that word linkage is just cut convex shaped cluster. And the same behavior have complete linkage and average linkage. So they are trying to cut clusters that have some convex shapes. Something like a blobs. While for single linkage, it is not important. So that is why single linkage is working better. If you just now recalled, we mentioned that single linkage can work when that data is non-globular data. This is just an example of non-globular data. Gandadzev shaper chunek convex paymanechkan. That is why so single linkage is the only one working here. And you can see that for the second example, these semi-moon structures. Again, single linkage is the only one which is working, because in other cases, again, the problem to have some convex clusters is becoming very important. Why? Because in these cases, we are trying to somehow minimize the objective function, which is very close to within cluster variation. So cluster standard deviation is becoming very important, while in case of single linkage, this is not important. So when you have such a strange shapes, and you know that this is the final result of your clustering, so you can easily use single linkage. But however, you see on the third example, single linkage is not working, because we have blobs here, we have convex shapes, and that is why all other average and complete and word linkages are working better. But the best one is actually word linkage. Why? Because you understand that this picture is exactly for k-means clustering. Here you see bad picture. So average linkage is not working. So worse result we have for complete linkage, because you see here some blue points together with these green points. The best result we have with word linkage. Why? Because this is the picture which is ideal for k-means clustering. And we know that hierarchical clustering is giving similar results to k-means clustering when we are using word linkage, because this word linkage is minimizing within cluster variation exactly the same as k-means clustering is doing. And for this example, no one is actually working. You see, single linkage is just giving you only one cluster. You can imagine because the corresponding dendrogram is very unbalanced. Here we have rather bad picture, so no one is working for these kind of observations. While for these blobs, so you see this is ideal example for any kind of clustering. We have 3 different blobs. These 3 different blobs are very far from each other, so it's very easy to perform clustering. That is why all 4 linkages are working just ideally. And not only hierarchical clustering, k-means, dbScan, all methods are working rather well for this kind of examples, because this is the ideal example for clustering. Without any visualization, all algorithms know how to perform this clustering. And the final example is very interesting. So randomly, just some random points without any visual clusters. And it's interesting how different methods are working. You see again that the single linkage is the best one. This single linkage is saying that you have only one very big cluster, and only you can see here some green and some orange points here, just something like an outliers. So average linkage is actually giving us some strange result. It's just dividing into 3 clusters, but there are no 3 clusters. The same with complete linkage. The same, by the way, with k-means clustering and with word linkage. Although it's trying to divide data into clusters, but you don't see any clusters here. So again, if you are trying to compare sometimes, although we are saying that single linkage is the worst case because it's always lead to some unbalanced trees, but you see on 3 different examples, it's just giving the best result. So this is what we have regarding hierarchical clustering. Let's jump to dbScan. If you have any questions, just go ahead. We can just stop for a moment here and then continue. So you already know 2 different clustering approaches, k-means and hierarchical clustering. So mini-batch k-means is just exactly the same as k-means, but with reduced complexity. So actually at this moment we have only 2 clustering approaches. And they are, as you see, they are working differently for different kinds of data sets.
Excuse me, how can we know that that Tarazakan approach is working for our data? I mean,
You don't know. You need to know that your data set, the features that you have are indicating some coordinates. You need to know it.
can we
From application, usually when you are starting to solve a problem, the description of the problem is saying what kind of data you have. The application is saying. In other, for our examples, as we are simulating data, we know that those data we can interpret like coordinates. In general, you need to know what kind of data sets you have. If you have pictures, then of course you don't have special clustering problem. You have something else. Application is always saying what problem you have. Is it special clustering problem or something else?
Okay, thank you.
Okay, stop sharing and then finding other presentations. So what we have here. You already have this presentation about dbScan. So here we have slides, unsupervised learning and dbScan. Okay, let's share this. dbScan. So this is density-based special clustering of applications with noise. So that is why we have dbSCAN. So you can think that this is density-based scanning, but this is not exactly the same. So they try to come up with some title. So they are naming it as density-based spatial clustering of applications with noise, and this is how you interpret this DB-scan. This is density-based clustering algorithm, and you can think about a family of algorithms which are based on densities. These are unlike k-means and hierarchical clustering, because in case of k-means and hierarchical clustering, we don't have such a notion of density. But in case of DB-scan, we are working with some densities of our observations, and there are different algorithms, a very huge family of algorithms which are somehow working with the densities. So they are trying to separate high densities from low densities. And you see the original article, a density-based algorithm for discovering clusters in large spatial databases with noise, from 1996. I uploaded this article so you can open and read it. Very interesting article. And this is, I have just copy-pasted some sentences that showing that this is the most popular algorithm of clustering. You see, is one of the most common clustering algorithms and the most cited in scientific literature. The most cited because you will find this algorithm applied for different applications. And what is interesting, in 2014, the algorithm was awarded the Test of Time Award at the leading data mining conference. This is a very well-known conference known as KDD, Knowledge Discovery and Data Mining, and an award given to algorithms which have received substantial attention in theory and practice, because this is the most cited in scientific literature and the most applied clustering approach. It's interesting that this simple idea that we have in DB-scan can become can gain this kind of popularity. So now general idea of DB-scan. So we understand that we have density, idea of density. So we are trying to separate observations with different densities. And what is interesting, you see that as density is the most important in this kind of clusterings. So the clusters found by DB-scan can be of any shape. When you are comparing with, for example, k-means, in k-means clustering, we need something like a blobs, while for DB-scan, it is not important. So clusters can have different shapes. And the central component, the central idea of DB-scan is the concept of core samples. So when you are performing DB-scan clusterings, you are labeling observations. There are three different kinds of observations. So we have core samples, we have boundary samples, and we have outliers. So the core sample is the basic idea within this DB-scan clustering. These are samples that are in areas of high density. So first of all, we are trying to capture high density domains, and all the points within these high density domains are core points, core samples. That is why when we are starting to perform DB-scan clustering, we are labeling data points, trying to understand where we have core points, because these core points are composing our clusters. So a cluster in case of DB-scan is a set of core samples, each close to each other. We will define how we are interpreting this closeness. So here we are measuring by some distance measure, and a set of non-core samples that are close to a core sample, but are not themselves core samples. These are boundary samples. So we have core samples and boundary samples close to these core samples. Core samples are composing the clusters. These non-core samples, known as boundary points, we are just joining to this cluster. However, you understand, we have some problems because we need to define what does it mean high density. we just said it and go ahead, but you understand that we need to come up with some ideas about density calculation. So we are assuming that, as usually in case of different clusterings, we have notion of distance. So as we started as a special clustering problem, so we can calculate distance by Euclidean formula. So we have Euclidean distance, but together with it, we need to understand how to define the density. So let's just go to the end of this slide and complete today, but let's also remember for our next lecture. So on Friday, we don't have lecture. We will meet together on Monday. So just remember that in case of dbScan, we have here two parameters, very important parameters. We have mean samples, the number of samples also known as pGAN. So we need to identify minimum number of samples and epsilon, also known as the radius, which define formally what we mean when we say dense. So we are, how we are defining, how we are actually measuring or dividing different points into core points and boundary points. So we are taking the single observation and drawing a circle with epsilon radius. So that is why this epsilon is very important. Then we are calculating the number of points that we have within this circle. If the number of points is equal or bigger than the mean samples, so if there are a minimum number of neighbors within this circle, then we are saying that this point is in a dense region and this is a core point. And we understand that within this definition, it is important to have this epsilon and minimum samples, because when minimum samples is, you are taking a smaller number, then you can work with smaller densities. If you are requiring bigger numbers, then you will label the corresponding observation as a core point when this point is in a dense region. So based on this epsilon and based on these mean samples, you are defining what is acceptable density for this dbScan algorithm. So this epsilon is the radius of the circle, and the minimum samples is the number of neighbors that you are waiting to see within this circle. If there are enough samples, then the corresponding observation is in a dense domain, in the dense region, and you are assuming that this is a core point. So higher n or lower r indicate higher density necessary to form a cluster. And we understand that in order to perform reasonable clustering based on dbScan, we need to define proper values for mean samples and for epsilon. And to illustrate the concept of density, so you see here three types of points. So we have core points, non-core points, and outlier points. So with core points, we understand how to work with these core points. These are points when we have the acceptable number of points within a circle with radius r. And just let's go to this picture. You see how this dbScan is working. So green cluster is constructed of different core points. You see how we are growing this cluster and joining different points together. Then we have this cluster 1 with blue observations. Again, this is some dense region. So blue cluster and green cluster, we can grow because we have here some dense points. And you see outlier, 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 just single points and no any neighbors. And here we have, again, some outliers. Why? Because when you are taking a circle, you see, for example, radius is 1, and you are waiting for 5 different observations. You see here, when you are taking this blue observation, you have more than 5 observations as a neighbors. For each green point, you have more than 5 observations. But for this red point, when we are drawing a circle with radius 1, you have only 2 observations. So this is not a core point. That is why you are not joining these to the clusters. So these are all red points are outliers, because within the circle with radius 1, there are no 5 observations. So that is why when you have 5 observations, you have core points and you are composing a cluster. These 2 clusters are separate. We will understand further how we are separating different clusters. But then if you have some points in a sparse region because you are not able to find 5 neighbors within the corresponding circle, you are labeling them as outliers and you are not clustering them. So it's very important to define this radius epsilon and the number of points mean samples 5, because otherwise when you are clustering, you can come up with final picture without any clusters, just with only outliers. Because when you are defining wrongly, all your points are becoming outliers, for example. And you can find such pictures in the Python codes that I already uploaded. When you are wrongly defining the corresponding numbers for parameters, you are ending up with wrong pictures. Okay, I think so. You can look in this example. So we have 3 different clusters, and you see these black points. Black points are our outliers because they are coming from a sparse region. And the points that you see, this red, blue, I'm saying blue, this green and yellow or orange. So decide which colors you want. You see dense regions, because this is density-based clustering. So 3 different clusters in 3 different dense regions. And then you have some black outliers in sparse regions. How many clusters we need? This is decided. DBSCAN is deciding how many clusters we will finally get. This is one of the advantages. You are not deciding how many clusters you need, but disadvantage that instead of the number of clusters, we have 2 other measures that I will say that not always easy to define. You will see from the corresponding notebooks that not always it's just reasonable values are easy to understand. Sometimes when you are clustering, you see only some outliers and some small clusters. There are some procedures we will talk about it. Also, Tigran will try to describe today because you have PSS. So during your PSS, you will continue to work with hierarchical clustering with maybe DBSCAN. There are a lot of different examples. And just play with the codes, with the notebooks, to understand how you can define those different constants and how these values are impacting the final picture of clusterings that you see. Okay, any questions just regarding this DBSCAN or hierarchical clustering? If you have, go ahead.
Պարոն Պողոսյան, մի հատ sense հարց, hierarchical clustering-ի ժամանակ, որ այն dendrogramները բանի tree նման բաներ են ստացվում, չենք կարա օրինակ random forest-ի խաղապար ընդեղ օգտագործենք, օրինակ random subset-ներ վերցնենք ու դրանցից հետո maximum բան vote անել cluster-ներ բաները ստանալու։
Machine learning-ում ոնց է, ամեն ինչ հնարավոր է, որ մի հատ գաղափար ես սպասում, հնարավոր է, կարող է լինի խնդիր, որտեղ աշխատի։
Այսինքն մենք այն բաները, linkage-ները հեշտ poker complexity-ով բան կընտրենք։
Չէ, դու հիմա նկարագրում ես մի հատ ալգորիթմ, որը որ կապ չունի hierarchical clustering-ի հետ։ Հա, hierarchical clustering ունի որոշակի կառուցվածք։ Հիմա դու պատմում ես լրիվ ուրիշ բան։ Որին կարելի է մի հատ առանցին անուն տալ, նայել գրականության մեջ կամ կա կամ չկա, հա, տենց։ Hierarchical clustering-ում ինչ որ Գաղափար կա։ Մենք ունենք հեռավորություն, մենք ունենք linkage, այդ linkage օգնությամբ սարքենք դենդրոգրամ։ Հիմա եթե դու ասես, որ դու ունես մի հատ ուրիշ ավելի հզոր clustering-ի ձև, որը որ ասենք մի միլիոն անգամ ավելի պակաս բարդություն ունի, դժվար է այդպես բան լինի։ Այսինքն միշտ էլ ինչ էլ հիմա հորինես, կամ վիճակը ավելի ես բարդացնելու, կամ ավելի վատացնելու ես, էլի։
Okay.
Կարող է մի հատ խնդիր հորինես, որի համար քո առաջարկած մեթոդը ամենալավն է աշխատում, ոնց որ միշտ հիշում եք, we have no free lunch theorem։ No free lunch theorem-ն ինչ է ասում, ասում է, որ քո առաջարկած մեթոդը բնականը լավ է աշխատում որոշակի տիրույթի խնդիրների համար, բայց in average, որ բոլոր հնարավոր data set-երը, բոլոր հնարավոր խնդիրները բերես ու performance չափես, բոլորը միջինում նույն ձևի են աշխատում ու դրանք բոլորը նույնն են, ինչ որ random search-ը։ Այսինքն այդ լավագույն բան եմ հորինել այսօր, որ աշխարհերեսին բոլոր խնդիրների վրա կաշխատի, no free lunch theorem-ն ասում է մոռացեք, այդպես մեթոդ գոյություն չունի։
Չէ, այստենց բաներ չասեք։
Դրա համար եմ ես միշտ ասում, ամեն ինչ machine learning-ում իմաստ ունի քննարկել, այնպես բան չկա, որ վայ, ինչ ես ասում, չի աշխատի, բարձա որ կաշխատի, կլինեն ինչ որ խնդիրներ, որտեղ այդ նոր հորինված մեթոդները հատուկ ինչ որ noisy data-ների համար կաշխատեն, բայց զգույշ եղեք։
Okay.
So, first of all, there are different ideas behind different machine learning algorithms. Then you can combine everything you want. So you can try different approaches. You can perform bootstrapping, then aggregation, then, all other baggings, boostings, growing different trees, different linkages. So we discussed only 5 linkages. You can invent more and more for your specific applications. Ոչ մեկ չի ասում, որ այս լինքիչներն են ու վերջ, ուրիշ բան անկարծ չօգտագործեք։ Լիք ուրիշ բաներ կարեք մտածեք։ You can decide different kind of linkages. So these are common standard classical examples and the common standard classical ideas. Ուրիշ ցանկացած բան, խնդրեմ կարեք մտածեք ու ձեր համար օգտագործեք։ Ձեր յուրահատուկ application-ի համար, որի համար միգուցե այս մեթոդները չեն աշխատում։ Ու կլինեն տենց լիքը խնդիրներ, որոնց համար չեն աշխատի։ Machine learning-ը հենց դրանով է լավ ու վատ, որ լիքը ազատության աստիճան կա, ինչ ուզում եք արեք։
Ես մի հարց ունեմ։
Ասեք։
Դիպիսկանի ժամանակ էլի pairwise distance-ները հաշվում, հետո տեսնում ա թե այդ էպսիլոնի շրջակայքում, եթե այդ n number կա, նոր իրան cluster-ը համարում, թե լրիվ ուրիշ ձև է։
Always when you have spatial clustering, the basic idea from where you are starting is pairwise distances. Ուրիշ տարբերակ չկա, there is no other way. So you need to come up with pairwise distances. So what you are doing, you are taking an observation, calculating all pairwise distances between this specified observation and the others, somehow sorting them. Then when you are taking this epsilon, you just know how many observations you have within this circle. You're just counting. If there are enough observations, then this is core point. If there are no enough neighbors, then this is not a core point. Միշտ pairwise distance-ները պետք է հաշվել, ուրիշ տարբերակ չկա. That is why all clustering approaches are rather complex approaches. Because you need to perform a lot of different pairwise distance calculations. Առանց դրա չի լինի. In case of hierarchical clustering, in case of k-means, in case of dbScan, and for all other spatial clustering approaches, you need to calculate pairwise distances. Then you are performing differently, of course. Different ideas are leading you for different clustering approaches, but the pairwise distances or distances based on some linkages is the most complex part of different clustering approaches. Այդ ամենաբարդ բանն է, միշտ զույգ-առզույգ հեռավորությունները պետք է հաշվել, ուրիշ տարբերակ չկա։ Կարող է լինի ինչ-որ ալգորիթմ, որտեղ ինչ-որ օպտիմիզացիաներ են արվում, բայց այդ օպտիմիզացիաները միշտ արվում են հիշողության հաշվին, so memory versus CPU runtime, այդտեղ ինչ-որ բալանս է գալիս։ CPU-ն մի քիչ քչացնում եք, որովհետև ճանապարհին ինչ-որ բաներ սկսում եք հիշել, memory-ում եք գրում։ Այդ կարա գացնի, բայց այդ memory հաշվին։ Հիմա թե Ձեզ ինչ է պետք արդեն կոնկրետ իմպլեմենտացիան կասի։ Because there are different modifications for different algorithms, so we have very fast algorithms, but consuming a lot of memory. Okay, any other things to discuss? Okay, then have a good day. We will meet on Monday. Bye-bye.
Տեսչեմ։
Thank you. Bye.
Հաջողություն։
Goodbye.